Welcome to solverfy.
Okay, in this problem we have a strange alternate universe where the Planck constant is 34 orders of magnitude or so larger than it should be in our universe. We have two students throwing a ball back and forth. They're separated by a distance of 12 meters. The ball is a quarter of a kilogram, and its velocity being thrown is 6 meters per second. So initially, we know that the uncertainty of the ball is within some cube of 125 cubic centimeters, which means that the perpendicular uncertainty in its position is 0.05 meters. So here's a little diagram. The ball is initially starting here. It's going up in the y direction to the other student, and it has some perpendicular uncertainty. And that uncertainty is only going to grow with time. So once it gets to the other student, there's going to be some uncertainty, some maximum amount of distance it could be off just by through quantum effects once it's thrown. So we're asked to find its uncertainty and momentum in the perpendicular direction and its final uncertainty and position after reaching the other student. This would give us some bound on how far it could miss just from quantum effects alone. So we're going to use the uncertainty principle, delta x, delta px, greater than the Planck constant, the reduced Planck constant, I should say. And because we're using this new value of h, we have to be careful not to use the much smaller normal value we would use for it. But h bar is still defined as h over 2 pi. And we also will use a little bit of kinematics. So let's jump into it. So to start, we can find the time it takes for the ball to reach the other student rather straightforwardly. It's going to simply be the y velocity over the y distance separating them. And we'll use this result slightly later. So it's 12 meters, or I should say, so 6 meters per second divided by, okay, need to be a little bit careful here. T is actually delta y over vy, of course. And just by doing some unit analysis, you can see that I was on the wrong track there. Okay, so delta y is 12 meters. Its velocity was 6 meters per second. So we have a time of 2 seconds. It'll take 2 seconds to reach the other student. And we'll use this result a little bit later. So now we can apply the uncertainty principle in the perpendicular direction. Delta x, delta px greater than or equal to h over 2 pi. Now, because we know that the ball is initially constrained within this cube with cube side length of 0.05 meters, we can use that as our delta x. We can solve for momentum uncertainty in the perpendicular direction. It's going to always be greater than h over 2 pi delta x. So plugging in the appropriate value for h, not the one we would normally use, and delta x equal to 0.05 meters for the cube length, we'll have a resulting momentum uncertainty of 0.21 kilogram meters per second. So clearly much, much larger than what we would normally expect in most of the problems we do. Okay, so let's box that. Now we can use a bit of kinematics. We know that any final uncertainty is going to be simply the initial uncertainty plus velocity, uncertainty in its velocity perpendicular times time. And we can actually ignore this because it'll be much smaller than it'll be small enough that we don't need to worry about it. So just considering delta vxt, we can replace delta vx by a momentum uncertainty instead. So delta px over m times rt. We know delta px, we know m, we know t. We solve for them all. We can plug all this in. We have a result of about 0.84 meters per second. times our 2 seconds, which gives us about 1.7 meters. So what does this mean? So if our distance was 12 meters, this predicts that just from quantum effects alone, when we throw the ball, the uncertainty, just fluctuations, will cause the ball to be as much as almost 2 meters off, so almost 16% off. So that would be it'd be hard to play sports in this kind of environment. Let's just say that. So these are the main results. We have uncertainties in momentum and position in this strange universe, which are much, much larger than they would be on Earth. Okay, thank you.